Advanced Conduction lecture series, and this is lecture 18. So I know that in the previous video there was some interruption, okay, due to some unavoidable circumstances, and due to that I apologize to all of you. So I will briefly recall the, not briefly, I will recall in detail that what I was discussing. So first let me give the lecture number here. This is lecture 18, right? Okay. So we were solving a question, a simple problem, not a simple problem, a practical problem that was telling that how the temperature profile will be in a rod with respect to time and space when the rod is being heated through the furnace continuously, right? So this was the situation, right? And here the rod was moving with a velocity u. It was entering from this side of the furnace and leaving through this side of the furnace, right? This was the situation, and I showed that why this graph will be like this and this. And I also told you that to be able to draw this kind of graph simply from your intuition is very important if you are going for an interview like BARC, DRDO and ISRO. Okay, so they actually look for your intuition very much, that how can you feel the thing, how can you feel that if the slope is going to increase or decrease, not by applying any formula but just by your understanding of the physical phenomena. Okay, so now after that I was talking about the two approaches by which we can solve this problem, right? So what are the two approaches? So the first approach is, here I will write here, approach 1. So approach 1, okay. So here the reference frame is fixed to the metal sheet, okay. And I gave you an analogy that consider yourself sitting on that metal sheet. So you think that I was talking about a point, okay, I was talking about a point or a segment on a metal sheet that is at time t equal to 0, it is just entering through this side of the furnace, right? So you consider yourself sitting here, okay, on the furnace. So then what you will see, that maybe at 12 o'clock I am entering in the furnace sitting on the metal sheet. So now when I am entering, I am suddenly being exposed from 25 degrees Celsius to an environment of 100 degrees Celsius. So that is a shock for me, right? And when I am passing through the furnace, maybe at 12:15, I am seeing that my temperature has been increased to 70 degrees Celsius. Obviously, you will not be alive after that, but still. So then when at 12:30 you are going outside from the furnace, your temperature is now almost 100 degrees Celsius. That is, it may be so maybe the temperature has risen up to the 95 degrees Celsius, okay. So that means if you are sitting on the metal sheet, then you are feeling, you are observing the change of temperature with respect to time, right? I hope that is pretty much clear. So that means if my reference frame is fixed to the metal sheet, then I will see, okay, the temperature profile is, or the temperature profile is changing with time, okay, changing with time. Now let me talk about approach 2. Okay, Okay, so in approach 2, the reference frame is fixed to the furnace. Okay, so now listen very carefully. If I again draw the 2D version of the problem here, so this is my furnace. Okay, this is my furnace, and my metal sheet I have drawn with white color. So let me maintain the consistency of the colors, and it will be it is not converting to a perfect rectangle, so let me draw it again. Okay, so the sheet is passing through the furnace like this, and it is an infinite sheet. I told you earlier also, right? That is the long sheet, a very long metal sheet is being passed. I told you that if you visit any kind of factory, then you will see that how these things happen. Okay, so it is passing through the furnace with a velocity of u. Okay, and the ambient temperature was Ta and the furnace temperature was Tf, right? Okay, so now you are sitting here. Okay, you are sitting here on the furnace. Now just literally imagine the situation, what you will be seeing. You know that the furnace is moving, you know that the furnace is flowing, that is correct, but literally would you be able to feel any kind of movement of the sheet? I mean, what should I say, what I am trying to tell is that if at 12 o'clock, listen this very carefully. Okay, so at 12 o'clock you are seeing that the temperature at this position is 40 degrees Celsius. So T ambient was 25 degrees Celsius, T furnace was 100 degrees Celsius. So 40 degrees Celsius is the temperature at a particular distance, maybe x. Okay, so had it been a finite sheet, had it been a finite sheet, then you could have said that my sheet is passing through it. Okay, my sheet is passing through it. So at 12 o'clock my sheet is like this. At maybe 12:15 my sheet has gone to this. At 12:30 my sheet has gone to this, and at maybe 1 p.m. my sheet has passed through the furnace. Now you can tell that if the sheet is finite, but the moment I say that the sheet is infinite, now you cannot say that, you are just you are just seeing the sheet all over the furnace at any at any time interval, right? Are you getting me that you are seeing the whole sheet throughout the furnace at any time interval because the sheet is infinite? Okay, a continuous metal sheet is passing through the furnace. Okay, that means if you are sitting here, then you are just seeing that there is a continuous thing that is flowing. Okay, that is flowing. Okay, you can see just up till this much, just up till this much. Okay, just up till this much you can see, and you are seeing that something is entering through here and it is passing through here and leaving through here, but that thing is not being completed. That thing is not being completed. The sheet is not being cut from any portion. So at any point of time you are seeing that something is entering with velocity u, that is passing with velocity u, that is leaving with velocity. So my point is, at any section like this, maybe at a distance x from the starting point, if the temperature is 40 degrees Celsius, now what do you think? If you are sitting on the furnace, would you be seeing that at 12 o'clock, if the temperature of this section is 40 degree, would you be seeing at 12:30, would the temperature be other than 40 degrees Celsius? Have you understood my question? That if at 12 o'clock the temperature at this section is 40 degrees Celsius, would that be the case that the temperature at 12:30 at this section has been changed? Is it possible if the furnace temperature is remaining same? That is not possible, right? So that means that if I am sitting on the furnace, then at any point of time the temperature distribution in this portion of the rod, in this portion of the metal sheet, I mean, will remain always same with respect to time. Okay, so if the temperature profile is something like this, then it will be like this at any time point. Okay, I hope you are understanding this. If not, please let me know. Okay, because this is a very important concept. So actually, I mean, what is happening? Actually, maybe I am considering only this portion of rod. So this portion of rod, it is entering, it is passing, and it is leaving. So while it is entering and passing this particular portion of the rod, it is the same. This is going to here and here and here, and ultimately it will go to outside of the furnace. So this portion will see a temperature change. This portion will see a temperature change. But the moment you are sitting here, maybe you are confining your attention only through this portion. Okay, only through this portion, or let me draw it like this, only through this portion. Okay, only through this portion. So when you are sitting here, you are focusing your attention only in this portion. Okay, so what is happening actually? A portion of the metal sheet which is at 25 degrees Celsius before entering in the furnace, it is going to 40 degrees Celsius when it is taking place of this position. Then this portion that was here at 25 degrees Celsius and it is now at 40 degrees Celsius, and it is now going forward, and then the temperature has been risen to 60 degrees Celsius. But the moment this portion is leaving this space, okay, the moment this portion is leaving this space, another portion that is behind it, it will cover this place, and it will again be subjected to a 40 degrees Celsius temperature rise. So at any time point at this position, at any time point at this position, if I measure the temperature at this position, that will be 40 degrees Celsius. I am for the last time repeating it because it is very important. So if my coordinate system is fixed on the rod, then I am this portion, this portion is me. So at 12 o'clock this portion is here having 25 degrees Celsius. Then it is going to this position at 12:15 and the temperature has risen to 40 degrees Celsius. Then at 12:30 it is at this position and the temperature is 60 degrees Celsius. This is the first case, that is if the reference frame is fixed to the metal sheet. Now when you are here, you have confined your attention only in this position, okay. So at 12 o'clock, okay, some portion of the rod that has come in this position, and now if I measure the temperature of this position, I get 40 degrees Celsius. At 12:15 this portion has been passed through and its temperature is 60 degrees Celsius. But if I measure the temperature at the same position at 12:15, I will still get 40 degrees Celsius, not 60 degrees Celsius. So that is the difference between two reference frame. In fluid mechanics also, I am giving you one more analogy in fluid mechanics that is very interesting. If you are sitting on a boat, okay, so maybe some of you have visited the Howrah Bridge, or if not Howrah Bridge, then any other bridge. So then if you see from the bridge down to the river, if any boat is moving, so if you see, then you will see that from the position from where the boat is passing, on that position the water is being disturbed. Okay, the water is being disturbed, but the moment you get on the boat, you will see that, I mean, if you see from the boat on the outside the water, you will not see any change with respect to time. Okay, so actually there is a course of fluid mechanics that I have started. I have explained this analogy in great detail when talking about the steady and unsteady flow. So no flow is steady forever. I mean, if you change the coordinate axis or the reference system, so then it can be a steady problem to unsteady problem, or unsteady problem to steady problem. So similarly, in this approach too, this becomes a steady problem, and we can say that with approach 2 we have converted it into a quasi steady problem. Okay, quasi steady problem. I hope you have you have understood it. If you haven't, then please let me know in the comments, because understanding of these things are main. Okay, okay, so now let us solve the problem. Okay, you are sitting here, so with approach 2 we will be solving the problem. Okay, so let us draw again the 2D view of the sheet, and in now I will not draw a full rectangle. Okay, so this is an infinite sheet, and I should also, I think, remove this part, then it is looking like an infinite sheet. From this diagram also, if I remove these parts, right, if I remove these parts, right, then it will look like something that. Okay, I will make this part dotted, right. Okay, so now you take any infinitesimally small control volume. So if this is my control volume, okay, and actually this is the start of the furnace, so this is x equal to 0 and this is x equal to L. Okay, so this is your nothing but a particular distance x. Okay, so now you have to just do one thing, that is the energy balance. Okay, so you tell me that what are the energy interactions here. So first of all, heat conduction, I will write q cond, and some q cond at x plus delta x is leaving. Okay, there is the convection heat transfer. We are neglecting here the radiation heat transfer. Okay, there is convection and there is energy flow because of the flow of the rod. Okay, so q conduction, q convection, and q flow I should say. Okay, because I cannot say here convection, actually q flow. Okay, so let us write that. So first of all, this is my delta x. Okay, so now let me write the energy interactions. So first of all, here I will get Qx conduction. Okay, I will write as a superscript C, okay, or CD maybe, conduction, and it is Qx plus delta x, again conduction, okay, and I will denote the convection by any other color, so maybe with green, okay. So here it will be convection, so Q dot Qx convection CO, or I should write CV, okay, array yaar, okay. And one more thing, okay, so this is a control volume and it is not a control system, that is, this thing is not the rod, okay, this is just a space, this is just a three-dimensional space like this, okay, this is just a space, not the rod. So now I will again write the flow with another color, so what should I choose? I can choose red, right? So if I have to do this, let me zoom a bit, okay. So yeah, I will write here, it will be, I have to write it a bit larger because I have zoomed it, okay. So it will be Q dot X flow, and it is going out again Q dot F x plus delta x, okay. Now I think it is fine, okay. So now I have to write the energy balance equation, so energy balance equation, so Q dot x is entering, Q dot x conduction plus Q dot flow is also entering at x, and what are leaving, okay. So this is a steady state obviously, because I have fixed my coordinate system on the furnace, so that will be Q dot x convection and minus Q dot conduction x plus delta x minus Q dot flow x plus delta x, okay. I hope this is clear, right? Okay, so now we can do one thing. So what you can actually do is, you can do the same thing, that is, you can so this will be plus, you can put this one here, okay, and this one here, and divide it by delta x to get del qx conduction delta x, right? But what I will do is, I will do some another approach, because you should be able to do the problems with different approaches. So I will do the same thing actually, okay, you will see. So this is Q dot convection at x. Now I can write this as at x plus del q cd at x delta x into del x, okay, plus the higher order terms, and similarly I can write the flow thing also like this, plus the higher order terms. So how I have written from this to this, just the simple Taylor series, okay, because this is what q conduction at x plus delta x. So if I write the Taylor series, this will be q conduction x plus delta x, this will be q conduction at x plus q conduction x delta x dx plus del 2 conduction del x2 plus into delta x square by 2 factorial, all these things. So after this term, all other terms I have written higher order term, okay, HOT, clear? Okay, that is fine. So now I can clearly cancel out these terms, right? So what I am getting, is Q dot convection at x plus CD, this one, plus higher order terms, okay, plus del QF, this one, plus higher order terms is equal to 0, right? Okay. So now if the solid is a Fourier solid, we can write this one as what? Minus KAX into del T del X, right? Now what is this one? Or let me write it with another color. What is this one? Can you tell me what is this one? So let me explain it. So if this is my control volume here, CV, this is my CV, okay. So what is happening? At this position at which the rod is entering, okay, the rod is entering from here and leaving from here. Now at this position, the velocity of the rod is maybe at ux, okay, and this u is actually a constant, so I will not write ux. So I have already told that that u is a constant, okay. So at this position, okay, that temperature is T subscript x, or you can write it as T bracket x, okay. And so here the energy is what? Energy is m c Tx, right, at this position of the rod, okay. Now if this is the energy, then I mean, what is the energy flow? Energy flow is m dot, right? So the mass flow rate of the rod, I mean, if I should say, so I will do an analogy with fluid, okay. So if this is a pipe, then a fluid is entering, okay, a fluid is entering with a velocity of u. So what is the mass flow rate? Rho A into u, this is the mass flow rate, okay. And I mean, what is the energy per unit mass? That is Cp into T, or C into T should I mean, I should say for a fluid, I mean for a liquid or a solid, okay. So rho AV is my mass flow rate into C into T. So C into T is what? Energy per unit mass, right? And this is the mass flow rate. So energy per unit mass into mass flow rate means what? Mass per unit time. So that means it is energy per unit time, okay. Have you understood? So the rod is going through this control volume, and while going through this control volume, this rod has a particular energy, okay. So if the rod at this moment is having q amount of energy, so then when the rod is going through this control volume with its own mass flow rate, it is carrying a particular amount of energy. So this much of energy is entering because of the mass flow rate of the rod, okay. Now at this position where the rod is leaving from the control volume, the rod is having I mean a different amount of energy, okay. So when it is leaving from here, again because of its mass flow rate, it will be leaving from the control volume with a particular amount of energy. So that is I am talking here, and that is I am calling here as flow energy, Q dot F, okay. So my flow energy is this one, right, and I can also write it as rho Ax into U into C into Tx. Okay, I hope this is clear. This is what? This is mass flow rate, m dot. Okay, and this is energy per unit mass. Okay, so this we got as rho Ax U C Tx. C is the specific heat of the rod. Okay, so if that is now clear, now one more term I have to define. So which term is that? That is nothing but our Q dot Cv. Okay, so I will take another color, maybe now this violet one. Why I have changed? Okay, okay, this is not violet. I will take this one. Okay, okay. So now let us see what will be Q dot Cv. Now if we see the 3D view again here, okay, if we see the 3D view again here, so let my control volume is this. Okay, I should draw it. My control volume is, okay, this one. My, it is not being very much visible, right? Can I change the color? Yes, I can change the color. So which color should I choose? I can choose maybe green will not be a, blue will be a right thing. Okay, here blue. Array, I have chosen blue. Oh no. So this is my control volume. Okay, this is my control volume. Clear? Now through which area convection is happening? Through which area convection is happening? Or let me draw it separately, otherwise it is being very untidy. Okay, so this one, okay, this one, so this is the sheet and practically it is an infinite one. Okay, now if this is my control volume, I am drawing it. Okay, this is my 3D control volume. Okay, okay, this is my 3D control volume. Now through which surfaces the convective heat flux will pass? Through this surface, through this surface, through this one, through this bottom one, and through this side one, right? So if this is my delta x, okay, and let us say that this CS area, the cross sectional area here is Ax. Okay, well, I don't need the cross sectional area actually. Okay, what I need is this perimeter. Okay, so this perimeter is what I need. Okay, this perimeter. So if this is my Px, P subscript x, so then what will be this total area? Okay, so this much area then I can found as my Px into delta x, where this is delta x, right? So the convective heat is passing through this area, this area, this area and this area, not through this and this, right? Through this area and this area the flow energy is passing and the conduction is taking place, right? I hope you are understanding, that is the convection is taking place from these areas, right? And the flow energy and the heat conduction is taking place from these much areas. Okay, so this is the area through which the convective heat transfer will take place. Now if my H is given, then what is the QCVX? That is clearly Px delta x, that is area, into H into Tx minus T ambient. Now be very careful, that is this can be T ambient minus Tx also. So if the temperature of the rod, and actually this will be here T ambient minus Tx, because the, and why that is so, and I should write it as T furnace, because I have already designated the TA for the ambient temperature outside the furnace. And I mean, why it is TF minus Tx? Because the convective heat flux is going from furnace to the sheet, right? So this I can, okay, and further if, okay, so I will say that assumption a bit later. This is Px delta x into H into T furnace minus Tx. Clear? So I have written all the terms. So now let me write this equation again. So what I will do is I will again copy. So in the examination also, if we could do this copy and paste thing, then it would be great, right? It would not be great, because in that case the questions will be set a more difficult. Okay. Okay, so now let me write the whole equation. Okay, so it will become, okay, so now I take the assumption, and then it is not an assumption, I mean it was told in the problem, or let me not take any assumption here. So Px H into Tf minus Tx. Okay, so this subscript means it is T at a, I mean Tx means T subscript x means temperature at a control volume that is situated at a distance x from the entry of the control volume. So into delta x plus, okay, del x of minus k x del t del x delta x plus HOT minus, now this I have to write as rho AX U C Tx into delta x plus HOT is equal to 0. Okay. Now if you take the limit delta x tends to 0, and you write the same equation, I will just copy and paste this. Okay. And then this will become what? So what you can do is, and you have to do is, divide all the terms by delta x before applying the limit, that you have to do. Okay, and even if you do it after taking the limit delta x tends to 0, it won't matter, because I have said that delta x is tending to 0, but delta x is not equal to 0. Then I can divide it anything by delta x is equal to 0. Clear? Okay, so now I am actually still applying the limit. Okay. So these terms will not change if I apply the limit, because these terms do not contain delta x. But what about these terms? Now you see, higher order term means it is having अरे यार, my phone's battery is dying. Okay, so now this HOT means it is having delta x square into something, maybe a constant C1, plus delta x cube into something, a C2. So this HOT and this HOT also, whatever these are containing, the power of delta x is more than 1. Okay, so if you apply this limit delta x tends to 0 here, then these all terms will go to 0. I hope this much concept you are getting, right? So then at that limit this becomes this one. Okay. Del x rho ax u c dx. Okay, and this is actually t subscript x is equal to 0. So now for the rod, for the not the rod, for the metal sheet, your ax is okay. So let us give the dimensions. Have I given already? I think no. So maybe the dimensions that I would like to give here is, okay, so this is my width w, okay, and this is my thickness, maybe small l, or I should write it thickness as small s maybe. Okay, okay, that is enough. So then my ax will be here a constant, and this will be small s into w. This is a constant, and my perimeter x will be 2 into s plus w, that is also a constant. Now again, if s is greater than w or w is much greater than x, s, I mean if I am talking about a thin metal sheet, so then my w is much greater than s for a thin metal sheet. Okay, for a thin metal sheet, then my px becomes 2 into w. Okay, is approximately clear. If I put these things into the equation to save time, I will just copy it. Okay, I will change this px with what, 2 into w plus s. Yes, I am not applying the assumptions yet. And what I can do with this term, if I say that my k is also a constant, I can write it as k into w into s into del square del x2. Okay, so I can, what I can do is I can shift this whole thing a bit here, and I can place this one here, 2 into w plus s. Okay, and for this one also, what I can do is, here all the things are constant, so I can write it as rho ax is what, this one, c u, okay, del tx del t del x. Okay, I think I have written it correctly. So this is my final governing equation, and throughout the equation I have done a mistake, a small, not a small mistake. Okay, that is my t is not a function of time, neither is it a function of any other coordinate or variable, so I can write it as capital D, not small d. Okay, so that was the thing. Okay, so this is my governing equation. This is my governing equation. Now, what about the boundary conditions? So you need two boundary conditions for x because it is a second order differential equation in terms of x. Okay. So the boundary conditions. So at x equal to 0, my t is equal to T ambient. Now the second boundary condition is actually challenging. Here I don't know the t. Okay. So one boundary condition can be that here my del t del x is becoming 0. So how can I say this? Have God said this to me in my dreams? No. How can I say this? See, here I have told already the reason that why the curve is like this. That is, the slope is decreasing. So the slope with x is almost 0 at the at the end of the uh, furnace, and that is very much practical, right? And that is why I can talk about this condition here. So one option is this, another option can be, okay, what can be another option? So another option can be, here maybe you don't know this temperature. Okay, you have to find this temperature. How can you find this temperature? By solving this problem. So I can give you another problem. Okay, so let us do that one also. That is a very interesting part. Okay, I am not solving this equation here. Okay, this is a simple ordinary differential equation. So here if I write the auxiliary equation, that will be d square into kw into s, okay, minus d square plus rho w s c u d plus what, plus, okay, so I cannot write it very easily, but if you write it as theta is equal to tf minus tx, okay, where tf is a constant, and you do all the substitutions and you convert it, then you can write it. Okay, so I will show you, don't worry, I will not skip anything. But for the time being, now let me solve the problem outside the furnace. Okay, so oh no, so uh, temperature profile outside the furnace. Okay, now again the same governing equation will be there with a minute change. Let me just copy and paste it. Okay, now the first change will be, now the rod or the metal sheet is having higher temperature than my ambient temperature. So my battery is now 10%, my phone's battery. I have to do it a bit faster. Okay, but all the other factors will be remaining same. Now here what will be the boundary conditions? Now at x equal to 0, again at x equal to 0, my temperature is something that I don't know, and at x tending to infinity, my temperature is tending to T ambient. Clear? So if I match, now what I can do is I can assume a temperature here. Let this temperature be TL. Clear? I can assume a temperature here and I solve this problem. Okay. So if I do that and I can match this solution with this one. Okay, I can match this solution with this one. Okay, I think it is not becoming very much clear. I hope that this is clear to you. Okay, what I am telling you, you can get the T from this problem. Okay, you can get the T from this problem assuming any temperature value here. Okay, assuming any temperature value here, and if the problem is giving you some feasible solution, then you can take this assumption here also. Okay, that is one approach. Okay, so that is how you can solve two parts of the same problem. So this was a very interesting one. Okay, so now let me show you a question. So this was the mid-sem question of IIT Kharagpur of 2023. Let's read this question. Okay, and you can take a snapshot also. Okay, this question 2. A plate of thickness 2L, so this is the thickness of the plate, is 2L, moves through a furnace with a constant velocity capital U and leaves at temperature T0. Okay, so here this is given. See, here this is given. I was talking about the practical scenario, but here this is given here. This boundary condition, this is given as T0 in the problem. This is given. Okay, so now where was the problem? Okay, outside the furnace it is cooled by convection only. Okay, and the heat transfer coefficient is H. Ambient temperature is T0. Assume that the plate is infinitely long. Write the two-dimensional non-dimensional steady state heat conduction equation for temperature along with the boundary conditions, considering x to be the distance from the furnace exit and y to be the distance from the center plane of the plate. Okay, if the temperature variation across the thickness of the plate is negligible, write 1D governing equations and find the dimensionless temperature Tx. Okay, so now you will be saying that okay, I know this part. That is, if the temperature variation across the thickness of the plate is negligible, then write the 1D governing equation and find the dimensionless temperature Tx. So in the second part of the question, what it is saying, that is, it is saying that is, if the temperature variation across the thickness means what? Across this thickness is negligible, then write the 1D heat conduction equation, and that will be nothing but this one. So this will be the answer actually. Okay, this will be the answer for the second part, and it is being told that you have to solve the equation. If you just derive this much equation, then you will get the 80% marks. Okay, so but now if you have to solve it, okay, so let me do the non-dimensionalization first, then I will go to the first part. And if my battery of the phone dies down, then still I will be continuing in my uh, iPad here. I will still write it, and just you will not be able to see me. I don't think that is a matter of concern for any one of you. Okay, so let me first non-dimensionalize the equation. Non-dimensionalization. So firstly, you would like to have this as your theta. I think by now you have enough experience to say that. Okay, so then you will not have any other constant here. Okay, because see, this equation is not a homogeneous equation, because you have 2 into w plus s into h into minus ta, and that is a constant. Okay, so just for the sake of simplicity, you want to make it a homogeneous equation, and what you will do is you will write here theta instead of this. So I will define my theta as tx minus ta by some t reference. Okay, and my x as x by some x reference. Okay, and my y as y by 2l. So that was the thickness, and thickness is along the y direction, and that is why I have taken 2l. So was the length of the furnace given here? No, it is not given. So I will write x reference. After that I can take any x reference. Okay, so if I now substitute the equation here, so let me again copy this equation. Okay, okay, so one more thing I can do, I can connect the charger to my phone. Okay, I was having the charger here, I was thinking that I am not having my charger. Just give me some time, I will just connect this. Okay, sorry for the interruption. Okay, and okay, the switch is on and the phone, is it charging? Okay, it is charging. Now you see, okay, so instead of this I will write what, theta into t ref, right? So now I will not again explain that how I am writing these things. Okay, that is, I think that is clear. This will be theta into t ref. This is okay, so here it should be x bar and y bar. Okay, so there should be x bar 2 into x ref square. This should be again theta into t ref. This should be x bar by x ref. Okay, so clearly, I mean, what was the short trick? Here I have in the denominator x ref, that is why it is x. Here if it has to be x bar square, I have to have x ref square. If you are still having confusion, just go to my previous videos, or otherwise you can simply apply the chain rule if you want to neglect that. Okay, so this is the non-dimensionalized equation, and here I can cancel this t ref out. Okay, and so this is my non-dimensionalized equation. Clear? And accordingly my boundary conditions will also be varied. So now let me come to the, okay, so in this equation now you can actually solve this equation very easily if you have, if you sorry, if you are remembering your uh, differential equation knowledge. Okay, so here the auxiliary equation will be minus kws into d square by x ref square plus rho ws cu, okay, into d by x ref. Okay, or I should write it like precision, and d I will write separately because d is the variable here in the auxiliary. So d square d. Okay, okay, another thing, that is plus 2w plus s into h is equal to 0. So this is the auxiliary equation here. Okay, and you see there is no constant here, so the particular integral will be 0. So from this equation you can find the d. So maybe my d is lambda 1 comma lambda 2. So your solution for theta will be c1 e to the power lambda 1 x bar plus c2 e to the power lambda 2 x bar. Okay, and your this is actually your complementary function, right? And your particular integral is 0, so this is actually your final solution. And you have to find the c1 and c2 by considering these boundary conditions. In the question it is given that this is given as t naught, and this will always be the boundary conditions, and you have already told that the plate is infinitely long. Now let us come to the I mean the first part of the question, and I will advise you that first you think by yourself that what it is telling. Write the two dimensional. Non-dimensional is okay. If you can write the dimensional governing equation, then you can convert it into the non-dimensional for anyways. So you have to write the two-dimensional equation. Steady state it is given, and actually the question is being a bit controversial. I mean, how can you consider it to be a steady state? It should be stating, okay, you can consider it to be a steady state if you are fixing your reference frame fixing your reference frame onto a fixed position and not onto the plate. Okay, so in our case I have took the fixed position as the furnace only. So here it is asking to write the two-dimensional equation. Okay, steady state heat conduction equation for temperature Txy. So in that equation I have written dTx dx, because Tx is only a function of x, but you have to write here Txy along with the boundary conditions considering x to be the thing. Okay, so now it is saying, okay, so again just let me draw the furnace first. Okay, and this is my metal plate here, and according to the problem that problem, okay, uh, this is x and this is y, this is my origin. See very carefully in the, that is in the question it is clearly mentioned that where you have to take your coordinate axis here, that is, see these lines, x to be the distance from the furnace exit and y to be the distance from the center plane of the plate. Okay, so x is starting from the furnace exit, that means my origin is at the furnace exit, and my y is starting from the center plane. Okay, okay, so that is why my coordinate system I am bound to take the coordinate system like this. You cannot take the y like here and x like here, because it is telling that the x is starting from the furnace. Okay, stroke. Okay, so now first of all, if I consider again the control volume here, okay, so I will cut one portion here and I take this portion and I will zoom it here. Okay, I will zoom it here. Okay, so here again I will write the energy interactions. That will be Qx conduction. Okay, there will be Qy conduction. again this will be your, okay. So okay, now one more thing, I will change my control volume a bit. Okay, now this is not my control volume. Okay, so okay, so I will take the control volume like this. Okay, so previously the control volume was having the thickness same as the plate thickness. By the way, in the problem it is given that is my plate thickness is 12, but now this is my delta y and this is my delta x and this is the control volume. Okay, because I have to take care of the temperature variation in y direction also, that is why I have considered this type of curve control volume. Now I will zoom it. Okay, I will zoom it and I will write the energy interactions. So first of all, okay, so here two energies will be there, let me draw accordingly. So q dot conduction CD x, q dot conduction x plus delta x. Okay, and again in this direction also there will be heat flow. Okay, so this was the only difference, this was the only difference from the previous problem. Similarly, I will have the q flow here, q dot flow x, q dot flow x plus delta x. Okay, so by the way this will be y plus delta y. Okay, but now here my control volume is inside the rod, my control volume is inside the rod. Okay, you see this is my control volume. Now you cannot say that from this phase and this phase q convection is going outside. So these are very important concepts. Okay, that is why this problem is very good. So you cannot say that is from this phase and this phase q convection is going out, you cannot say that. What you can say is that is my energy is flowing, energy is being converted. Okay, because you can see if the control volume is inside the rod, then there is no question of heat convection. Heat convection will only happen at the surface, at the interface of the air inside the furnace and the rod. So in the previous case my control volume was like this, and I could take the control volume like this because I neglected my temperature variation in this direction. That is why I took my control volume like this. Now these phases of the control volume is directly subjected to convection. That is why you could say that my convection heat transfer will be there and there will be no conduction heat transfer in y direction. But now here these are the energy interactions. So now it is your homework to reach the governing equation, and I will write the governing equation. Okay, but in the examination hall you are supposed to derive it. So the final governing equation for this problem will be, okay, I have told you all the concepts. Okay, that what will be the case. So I will copy this. Now the difference will be that is no heat convection term will be there, and one more, there will be K. Okay, some area AY, I will say that what it will be D. Okay, now it will be del, all the terms it will be del because it is a function of x as well as y. Okay, and it is better if you don't write the subscript x here. You can write t of xy here if you want to write something, t of x comma y. Okay, del x, and here also you have to write del 2T del y2. Okay, and what will be this ay? Okay, so if the thickness, if the width, so is the width given in the question? The width is, I think, not given in the question. Okay, the width width is not given in the question. You assume some width w. Okay, so if it is a thin plate, then w will be much greater than thickness. That will be another thing. And because the thickness is given as 2L, so instead of this S, I will write here 2L. Okay, and this will be here, this will be here my what. So if I see this control volume, okay, so this control volume is like this. Actually it is having a width, okay, it is having, this control volume is actually like this. Okay, so it is having the width d, I should write here, it is having a width here w, not d. Okay, so my area y should be this area, right, this area, and this is what, this w into this delta x, w into delta x, right, w into delta x. And what will be my ax now? Ax will be this area, this will be w into delta y, right. So here I have to change, it is being hanged or what? Okay, so this will not be w into 2L, this will be w into delta y, this is ax, and this will be w into delta x. Clear? I hope that is clear. Okay, so Kax, actually the thing will be what you will be getting. So after that it will be multiplied by delta y, it will be multiplied by delta x. Okay, and here this will be not be w into s, right. What it will be? It will be this area, right. The energy flow is happening through this area, right. Energy flow is happening through this area, the same, that is the conduction area, and that will be again here w into delta y, and again you will have a delta x multiplied by this. Okay, now what you will be doing is you will be taking the limit delta x comma delta y tending to 0, and you can see that I can divide the equation by delta x delta y, because delta x and delta y are tending to 0 but they are not equal to 0. Then the final equation that you are getting is minus k, okay, del t del y2. You see w also you can cancel out, okay, minus k del 2t del x2 plus rho cu del t del x is equal to 0. So this will be your answer for the governing equation part. And what is the boundary condition? Boundary condition is 1. So you need 2 boundary condition for x, 2 for y. Okay, so for y equal to, okay, so at y equal to minus L, at y equal to minus L, okay, you can write my minus k del t del y. So now be very careful about what, that is my heat will be going like this, heat will be going like this and this, okay, this and this. So at y equal to minus L means this phase, heat is going like this. I have explained ample amount of times that how to write the boundary conditions at these types of phases. So if I am telling my K delta T delta Y is the positive heat flux, then what is the direction of that heat flux? It is in this direction. So if I have to write the heat flux in this direction, it will be K del T del Y, right? So that is why I will write here minus of minus K del T del Y is equal to H T at Y equal to minus L, okay, for any x, minus T ambient. This is the boundary condition at x equal to minus L. Now at x equal to, sorry, at y equal to minus L. Now at y equal to L, this will be minus K delta T del Y is equal to H T Y at L x minus T A. Now can you visualize that is the problem is totally symmetric about the x-axis? That means my temperature profile will also be symmetric about the x-axis. That means I can also write, I mean if I drop any one of the boundary conditions out of 1, 2, another options, so as option I can write as option instead of 1, 2. I am writing this because don't tell yourself that I have 3 boundary conditions. You can't have. Okay, so you can write at y equal to 0, my delta T delta Y equal to 0. Ideally you should have checked the, I mean boundary condition. Okay, sorry, you should have checked the symmetry. Okay, ideally you should have done that. Clear? Okay, so now this is the boundary condition for y. So what will be the boundary condition for x? So boundary condition number 3, it is given. Okay, that is at x equal to 0, my T is equal to T naught. The furnace temperature at, sorry, the temperature of the metal sheet at the furnace exit is given, and as my x is tending to infinity, my T is tending to T ambient. So this is the answer of the first part. Okay, now only thing is you have to derive this. You have to derive this. So derive with a very cool mind. Derive with a very cool mind. Have this 3D control volume in your mind. So what will happen? Just tell me. I mean, what will happen here? So everything will be the same, this Q flow, but you have to take care of the fact that is my AX here is not equal to W into S as I have written in the previous problem. So that is why I always tell everyone that please don't try to mug up any problem. If you want to mug up something, then mug up the concept. That is, I have to do energy balance. You can mug up this thing that in most of the heat transfer problem I have to do energy balance. Not only in conduction, but when you will be studying convection, radiation, you have to do the energy balance. You mug up this statement, but don't mug up that I studied that this area will be W into S, but why it is W into delta Y? So it is W into delta Y because, my friend, beta, this is this area through which the flow energy and the heat conduction in x direction is passing. And what is this area? Is it W into S or W into 2L? No, because now this thickness is not 2L, this thickness is what? Delta Y. So that is why my AX is here delta Y. Similarly, what is my AY? AY is this area, and that is W into this much is delta X. Now you will ask that then why this delta Y, delta X, and here also delta X, I mean how the hell these are coming? These are coming because you just remember I am solving the problem at least 50%, and the rest of the 50%, that is the official pen and paper work, is remaining for you. So you see this part into delta X is already there, into delta X is already there. And why it is this? Why it is this? Because you see the energy interactions, it is Qx that is passing through this phase, and Qx plus delta x that is leaving through this phase. So ultimately when you will be performing the steady state energy balance, this will be this minus this, then what will be remaining? It will be del qx cd delta x del x into delta x. So it is this delta x, it is this delta x which I am writing here, which I am writing here. Similarly, when you will be performing the energy balance for this y direction conduction, you will get this minus this minus this, then you will be getting del q dot y del y into delta y. This delta y is what I am writing here. I hope now it is clear to you. I have almost told the 100% logic, 100% steps. You have to just do it by yourself once in your copy. Okay. So never try to mug up any problem. Try to mug up the, okay, you can try to mug up the approach also. That is okay. If I have given a furnace, I will first see the assumptions that is given or allowed in the question paper. If no assumption is given, you can take also assumptions. You will see in the top of the question paper, it will be written that take the assumptions as you feel, but justify the assumptions. That is, I will take that my W is much greater than the thickness, because you are talking about a thin plate. Okay, so I am talking that just by seeing the question, first see the assumptions. The moment you are comfortable with the assumptions that okay, I am being told that my thickness is very small, then I can say that my temperature variation in y direction, I can neglect that. Okay, so and then you have to go for the energy balance. You have to go for the energy balance. Don't try to approach like this. Okay, I have heard in that lecture that the equation is looking like something, this equation looks like something this. Okay, so then let me start by writing the equation that I have marked up, that is this governing equation, and let me try to change some here and there. Even after that, even you get to the right governing equation, you will be not given the marks. You have to derive from the scratch. That is what the examiner asks. Okay, now the next point. So in the first part, it is given that you have to derive the two-dimensional temperature profile, and in the second part, it is given now if the temperature distribution is neglected along the y, along the thickness, then what will be the case? Then some students will think that okay, then I have to do some manipulation in this governing equation, then I will get. And what they will do is, okay, because my temperature profile is not varying with y, my answer will be just I will make this 0 and that will be my answer. No, that will not be your answer. Okay, because you are, okay, that could be your answer. That could be your answer if you are writing still the 4 equations. Still the 4 equations. But now in these 4 equations, you will not have these boundary conditions. You will have at y equal to minus L, my T is equal to T at x. At y equal to L, my T is equal to Tx. Then your answer is correct. Have you understood? That is, if you say that this will be 0, that is correct. Then this is my governing equation. Okay, that is perfectly fine. That means here this is your governing equation. If you write this is equal to 0. But the moment you are writing that, you are bound to write these 4 equations, but now at y equal to minus L, T will be equal to Tx. At y equal to L also, my T will be equal to Tx, because my T is not varying with x. Then why I am writing these boundary conditions for y? Because you have taken your control volume like this. Your control volume is varying both in x and y to cover the whole rod, to cover the whole metal. But in the question paper, it is given that you have to write the 1D governing equation. 1D governing equation. Then you cannot write, then you cannot write this thing. Then your control volume has to be changed. Then your control volume has to be changed from this one to this one, the control volume that I have drawn earlier. So the second part of the problem, the answer will be this. Okay, and finally to solve this governing equation, okay, so solving this governing equation is not actually very easy, okay, because it is a partial differential equation and there are separate methods, okay. So even if you don't solve this governing equation, and I hope the examiner has not asked to solve the equation. See, here it is written, write the two-dimensional, non-dimensional. Okay, so you have to non-dimensionalize the equation. That is your homework. At least that you have to do by yourself. I will not tell anything about that. So write the two-dimensional, non-dimensional steady-state conduction equation, and you are not asked to solve that. Okay. So with that, I have covered this special type of problem. This is not a special type of problem. You can also consider any problem by yourself. For example, if I am telling a problem that is in cars we have clutches. So I am sure that during your B, when you were studying the brakes and the clutches, so there were an analysis when these two clutch plates are being rubbed like this, there will be a heat formation, right? And there was an equation, that is the friction work that is being done here, that was being equated to the heat convected to the coolant that is being passed to cool the clutches or the ambient air if no coolant is used. Now if you have to do a detailed analysis, that is you have to consider the whole circular plate and you have to find the temperature distribution in the circular plate, and you know that there is a frictional heat generation in the friction lining, so this is also a heat conduction problem, right? So if I now tell you that okay, you solve that problem, you have to think from scratch. Okay, so this is a very much complicated situation. How can I simplify this? What assumption can I take? So because of the clutches are very thin, can I neglect the temperature distribution in the length part? Can I do that? And also maybe I mean like assumptions like this only. Okay, you have to think about that as a practical engineer. Okay, so in the next I think in the next 2 to 3 lectures, maximum 4 lectures, in next 4 lectures I will end this advanced conduction thing. Okay, for now, I am saying for now. If in the future I feel that I need to add something, then I will update this series. Okay, but up till now I will conclude this series within, I think it will be completed within 3 lectures, but max to max 4 lectures. Okay, so in the next 2 lectures we will be seeing a semi-infinite plate, lumped parameter analysis. Lumped parameter analysis you have studied in your BE, but still I have to cover it here because I have promised that if someone is expecting the things from very basics, if he or she is expecting that I will cover my GATE examination also, then I know that this lecture series is too much for GATE examination. Okay, now that is why I don't refer anyone who is preparing for GATE this thing. Okay, this lecture series. Okay, so we will see the semi-infinite things. There is something called Stokes first and second problem. So the Stokes first and second problem we study in the fluid mechanics generally, but the same problem, the same governing equation, the same boundary conditions, just there was fluid flow, and here we will study heat flow. Okay, there was velocity as unknown, and here we will have temperature as unknown. Okay, so we are at the end point of our advanced conduction series. Please write if I have missed anything. Okay, because the thing is, the moment I teach you something in that lecture, okay, after that I don't do any self study because I am busy with so many things. So what I what I teach you here, I mean just on spot. I don't have any practice, any revision just before teaching. Okay, so if I am missing something, then please notify me in the comment box as soon as possible so that I can cover it. Okay, so that goodbye, take care, and thank you.